Thank you for the nice introduction, and thank all of you for being here to participate. So I wanted to talk a little bit today about some of the work that I've done looking at carotenoids and breast cancer, but I also wanted to give you a little bit of background building up to this so you can understand the context of this. So I don't have any disclosures to discuss, and I wanted to address in this lecture looking at potential mechanisms by which carotenoids may be acting to reduce breast cancer risk, to understand the current evidence for the role of carotenoids in breast cancer, and to recognize the potential for carotenoids to be acting on particularly aggressive breast tumors. So I wanted to start with, actually this is building on Dr. Garland in epidemiology, but I wanted to discuss a little bit about study designs, and then looking at breast cancer epidemiology to understand the risk factors and disease heterogeneity so that there's a context to understand the carotenoids relationship. And then we'll go into the carcinogenesis and the opportunity for carotenoids to intervene. And then looking at the pooled analysis of circulating carotenoids and breast cancer and some of the more intricate ways we can look at timing of exposure and breast cancer and disease subtypes. And then I just wanted to end with a few of our more recent dietary findings with breast cancer. So to start with, if we're interested in diet in terms of cancer prevention, what we really want to know is somebody's diet when they're healthy before they develop disease. So does their diet lead to a reduction in the risk of, in this case, breast cancer? So the study design that I focus on to get at this relationship of diet prior to the onset of breast cancer is to use a prospective cohort study. So I work within the Nurses' Health Study and Nurses' Health Study 2, and these cohorts, the first Nurses' Health Study was begun in 1976, and it includes almost 122,000 women who at the time were between the ages of 30 and 55, and we continue today, 40 years later, to be following these women. And the way we follow these women is that every 2 years we send them a questionnaire and ask them lots of detailed questions about their reproductive history, anthropometrics, what medications they're taking, and any new disease diagnoses, which are then followed up by confirming them by medical record review. And every 4 years, we have included a food frequency questionnaire designed by Walter Willett to ask them about their usual dietary habits. And then about every 2 to 4 years, we also query their usual physical activity. And importantly, for what I like to research is that in 1989 to 1990, among about 33,000 women, we collected blood samples and archived them in our storage facility, and then we can continue to follow these women throughout the cohort. And about 10 years later, we collected a second blood sample from about 18,000 of these women. Now, among the women who have developed breast cancer, we have also had them donate their tumor tissue so that we can examine it in more detail and sometimes get at a little more of the underlying molecular characteristics of their tumors than we can get from their medical records. So the Nurses' Health Study 2 is a younger cohort of women that was started in 1989 when the women were between the ages of 25 and 42. And this cohort contains about 116,000 women. And similar to the original Nurses' Health Study, we collect information by biennial questionnaire. We've collected much of the same information as we have in Nurses' Health Study, including diet and physical activity. And in this cohort, we've also asked them to try to recall what their physical activity and dietary patterns were during high school. And then we continue to follow these women throughout their adult life. And similarly, we also collected blood samples in almost 30,000 women in this cohort, and then about 10 or 12 years later collected a second blood sample in a little over half of the women. And similarly, we also have their tumor tissue once a woman develops breast cancer. So what we can do with these stored blood samples, and Dr. Garland mentioned this, going to Washington County to collect these blood samples, and then we continue to follow the women, is that we can understand what their exposures were when they were healthy, so before anybody develops any disease, and we can go back and look at their blood samples. So some of these women will develop breast cancer, and then some of these women will remain healthy. So we can pair them together and try to understand what their exposures were like prior to disease development and how they might differ between women who became cases and women who remained disease-free. And using the 2 blood collections, we can try to get at an understanding of the importance of timing. So with the, with the first collection, we can look at proximate measures, so understanding the exposure within about 10 years of the diagnosis. And with the second collection, we can do the same thing. But with the first collection and later disease diagnosis, we can look at their blood levels in 1990 and look at diseases that were diagnosed 10 to 20 years later to help us understand, is it something that is more immediate, or is it something that's a longer-term exposure that's more important? So now now you have a sort of a refresher on study designs and what aspects of these are important. I wanted to talk a little bit about breast cancer. So I know Dr. Ho brought this up, and we discussed it a little bit during the panel this morning. But this gets at, again, this issue of the fact that there is worldwide variation in the rates of breast cancer. So there's a nearly 3-fold difference in the rates of breast cancer between places like Asia and places like North America. So some of the changes that we can see with migrants, as again was discussed earlier this morning, we can see that the rates of breast cancer increase as women move from this dotted line, or the Japanese women living in Japan, and then Japanese living in Hawaii, who then develop higher rates of breast cancer. The top red line are women, U.S. Caucasian women living in San Francisco, and then the line in between are Japanese Americans who have emigrated to San Francisco. So this suggests that there is something modifiable going on. As these women emigrate, they develop not just dietary patterns, but other societal changes. Physical activity was mentioned this morning as well. But clearly there is something in addition to genetics going on. So this is an area of great interest to try to understand what these factors are. So we know, quite a bit about some breast cancer risk factors, and they occur across the life course. So there are factors clearly that are genetic, and factors that happen intrauterine in terms of exposure. And the height and growth velocity of children through adolescence affect later breast cancer risk. At an age that a woman goes through menarche also affects breast cancer risk. So the earlier in age of menarche, the higher the risk of breast cancer later. We know that later age at first birth increases the risk of breast cancer. Breastfeeding can reduce the risk, particularly for some of the more aggressive triple-negative breast cancers. Parity, having multiple children, can reduce the risk of breast cancer, again, especially if the age at first birth is young. Then, sort of cumulatively reflecting a woman's lifetime exposure to estrogens and other hormones, later age at menopause is associated with a higher risk of breast cancer. So a lot of these risk factors we know them, but they are not necessarily modifiable, and some of these have changed over time, just given the way our society has changed over time. But there are some factors that are modifiable, and a couple of them after menopause include the use of hormone therapy and BMI, or excess adiposity. So just to give you a sense of some of the modifiable factors, and this is a particular area of interest of mine, one of them is looking at weight change. So we know, looking at weight change across the life course, that women who gain weight across adulthood are at a higher risk of breast cancer, as you can see here, and this is women who are postmenopausal. And there is some suggestion of an inverse association for women who lose weight across adulthood and their risk of breast cancer. And again, since one of my areas of interest is modifiable risk factors, one of the things I'm interested in is, does it have to, is there something that can change later in life? So we looked at whether weight change after menopause is associated with breast cancer. And this is looking among women who have not used hormone therapy, because this is where you can see the clearest relationship between obesity and breast cancer. So weight that's gained after menopause is associated with a higher risk of breast cancer. And women who lose weight, and in the dark blue bars, women who lose weight and are able to maintain that weight loss after menopause, are at a lower risk of breast cancer. Now, physical activity, we can see adulthood physical activity, higher levels, is associated with a lower risk of breast cancer. And this is from the Nurses' Health Study, and interestingly, a lot of these women, their primary form of exercise is brisk walking. So you don't have to be a marathon runner to appreciate this benefit. Even some good old-fashioned walking helps. And again, looking at can this risk be modified after the time of menopause, we looked at women and their levels of physical activity prior to menopause and whether they changed after menopause. So compared to women who had low levels of physical activity, in both before menopause and after menopause, women who had low levels of physical activity before but increased their risk of physical activity afterwards had a lower risk of breast cancer. And similarly, the women who had high levels of physical activity at both time points were at a lower risk of breast cancer. But one of the things that I appreciate about this is that it's never too late to change some of these risk factors. Another one that's modifiable is alcohol, and this is one of the most well-established sort of dietary components of breast cancer risk factors. And it's a consistent increased risk of breast cancer with higher alcohol consumption. And one of the things that's striking is that even at lower levels of about a drink a day or less, you can see an increase in risk of breast cancer. So I wanted to get a little bit into disease heterogeneity, which we actually talked about a little bit earlier with Dr. Vedat's talk. And she mentioned being able to subtype tumors by their molecular characteristics. So almost 15 years ago now, some analyses were done looking at the molecular characteristics and gene expression of the tumor, and these can then be classified into different subtypes. The luminal subtypes, luminal A and luminal B. The ERB2 here is the HER2 positive, and then the basal subtype includes the triple negative cancers that were mentioned earlier. So, and as was discussed earlier, these subtypes are associated with different survival. So we can see in the dark blue line, these are the luminal A tumors. And as Dr. Vedat had mentioned, the luminal B tumors have slightly worse prognosis. And then all the way down to the pink here, the red is basal and the pink are HER2 positive. Now, we don't have the luxury of being able to do gene expression analyses on every tumor that we get in our epidemiologic studies, or even for all of the cases that we have. So what we can often do is sort of simply classify by expression of estrogen receptor. So we can have classify estrogen receptor positive tumors and estrogen receptor negative tumors. And we can use a few other markers to help us get at the subtypes, the luminal and the HER2 and triple negative or basal-like subtypes. So these include progesterone receptor, HER2, using grade of the tumor, or the marker Ki67, which was mentioned this morning in terms of a marker of proliferation, as well as cytokerotene 5/6 and EGFR. So when we look at tumors that are either estrogen or progesterone receptor positive, we call those hormone receptor positive tumors. If they're also HER2 negative and a low-grade tumor, these are considered the luminal A tumors. And if they're hormone receptor positive and either HER2 positive, or if they're HER2 negative and have a higher grade, these are considered the luminal B tumors. And then on the ER negative side of things, we have the ER negative, PR negative, but HER2 positive, or the HER2 enriched tumors. And then tumors that are negative for ER, PR, and HER2, triple negative. And we also use the additional classifiers of the CK56 or EGFR being one or the other positive to call these basal-like tumors. And then tumors that don't have expression of any of these 5 markers, we sort of dump into an unclassified category. So that gives you a little bit, and these subtypes will be important as we start to look at some of the evidence of carotenoids and breast cancer. So now turning towards the carotenoids, this is, I wanted to sort of come back to the simple, very oversimplified model of cancer initiation and promotion. So we know that, normally cells replicate and things go well, that's great. but it's possible that we have exposures that can muck with this system. So, ionizing radiation can induce DNA damage and oxidative stress. Regular cellular metabolism can also induce oxidative stress, as well as estrogen metabolism, exposure to alcohol, inflammation, and the list goes on. So a lot of these can contribute to oxidative stress or directly damage the cell. And once we have some damage in the cell, clearly there are a lot of other events that need to happen, or in some cases there are events like the epigenetic events that can happen to damage the cell as well. In any case, as these mutated cells get replicated, ultimately downstream, these can turn into a tumor. So thinking about where carotenoids come into play in this is that carotenoids can act as antioxidants and impact and lower the exposure to oxidative stress, and therefore, cut out the rest of this cascade, we hope. Alternatively, carotenoids can be acting on reducing the promotion in cells. So if there are cells that are already mutated, then these can be inhibited by the action of carotenoids, and again, hopefully interrupt the downstream consequences there. So sources of carotenoids, I'm sure I don't need to elaborate in the audience here, but as you know, in plants there are more than 600 carotenoids that have been identified, and these 6 that are listed here are the most prevalent in the human diet and make up about 90% of the carotenoids that are measurable in blood samples. Now, thinking about carotenoid bioavailability, there are certainly factors that affect that. So not everybody is going to have the same internal dose of carotenoids based on the same amount of intake. So one thing that affects these, given that they're fat soluble, is the fat intake along with the fruits and vegetables that are rich in carotenoids. So this was a study conducted about 10 years ago, or more than that actually, that looks at the carotenoid bioavailability. So it's a change in carotenoid concentration on the y-axis here, and on the x-axis is the time after eating, in this case, salad, but with 3 different groups. So in the triangles here, the bottom level in each of these graphs, the salad had fat-free dressing on it. So you can see that this had quite an impact on the lack of carotenoids making it into the bloodstream. And then the open circles are salad consumed with a reduced fat salad dressing. And then the top filled in circles are a full fat salad dressing. So you can see here that fat intake really does affect the bioavailability of carotenoids. Another thing, you can see lycopene down in the bottom here. But we also know that for something like tomatoes, cooking the tomatoes can increase the bioavailability of lycopene. So there are a lot of, there could be inter-individual differences in terms of the preparation and consumption of fruits and vegetables that could affect the carotenoid bioavailability. We also know that there can be inter-individual variation in terms of absorption and metabolism of carotenoids that can impact levels of carotenoids within the body. So here I'm showing the pathway for these provitamin A carotenoids, alpha-carotene, beta-carotene, and beta-cryptoxanthin. And these get cleaved by an enzyme, the beta-carotene 1515 monooxygenase enzyme. So with central cleavage, these are ultimately turned into retinol. But we know that about a quarter to a half of the population are considered poor converters. So for the same dose of beta-carotene, they have less retinol as a result. And this is thought to be involved or be due to genetic variation in the BCM01 gene. And we had a student several years ago who looked at whether circulating carotenoid levels in blood samples were related to genetic variation in this BCM01 gene. And what she did was developed a gene score looking at the SNPs across BCM01. And you can see, so this is looking at quintiles of the gene score, that there is quite a bit of variation between levels of the carotenoids based on somebody's genetic profile of BCM01. So we can see it for beta-carotene, alpha-carotene. You can barely see this here, but it was significant. And beta-cryptoxanthin, and then also lutein zeaxanthin, which is not a provitamin A carotenoid, but BCM01 does seem to have an effect on lutein zeaxanthin levels as well. So given the differences in preparation, absorption, genetic differences, thinking about how we measure carotenoids in an epidemiologic study becomes more important to try to understand what somebody's real internal dose is. So thinking about this, so one way of measuring carotenoids is using something like this, which is a snapshot of the food frequency questionnaire that we use in the Nurses' Health Study. And I know it's totally illegible, but I just wanted to have you have a feel for what it is like to try to fill this out. So the top section are fruits that are listed, and the bottom section are vegetables. And across is the frequency that these are consumed. So people will, as what your usual diet, do you consume these less than once a month? Do you consume them about once a month, once a week, daily, et cetera? So we can use this information to then either look at fruit and vegetable consumption itself, or we can calculate micronutrient intake from these using the USDA database. And one thing that's nice about this is that it's more possible to directly translate this in terms of a public health message. And I think it was Dr. Hardy this morning who was saying, I focus more on foods than the micronutrients themselves. So this is an easier way to get at that, what is more translatable. The other nice aspect of this is that it's easy to hand out a piece of paper to 100,000 women compared to trying to measure blood samples in that many women. So you can implement this in a large population for relatively low cost. But on the flip side, using blood samples to measure carotenoids, we can get at the actual micronutrients that are probably of biologic interest, in this case, looking at the carotenoids individually. And as I noted, this is now an integrated measure of somebody's intake, the preparation of the food, their individual absorption, and metabolism of the carotenoids. So in a couple of very large pooled studies of cohort studies using something like the food frequency questionnaire and looking at both fruit and vegetable intake as well as specifically carotenoid intake. There are a couple of students at the School of Public Health at Harvard that were able to look at this, and breast cancer. And this has something like 12 or 15,000 cases of breast cancer. So looking at fruits and vegetable intake, remember we talked about ER status, so estrogen receptor status. So in the blue bars are ER positive tumors, so those are the ones that are hormone responsive. And in the red bars are the ER negative tumors. So we can see that higher intake of fruits and vegetables is associated with a lower risk of specifically the ER negative breast tumors. And then when we look at calculated carotenoid intake, this is using beta-carotene as an example, we see something similar. So women with higher intake of beta-carotene had a lower risk of the ER-negative breast cancers. So that's what we can do in some of the dietary studies. And as you can see, the relationship is fairly modest. So in some cases, it's easier to detect an association that's stronger unless you have thousands of cases of breast cancer in very large cohort studies where you can start to try to tease this apart. So then thinking about how we measure this in circulating carotenoids, when I started to look at this in sort of the late 2000s, there were about 8 relatively large cohort studies that had been published that looked at the relationship between plasma or serum carotenoids and risk of breast cancer. Now, these were all nested case control studies. So if you remember, these are looking at blood samples that were collected before anybody got breast cancer, and then comparing blood samples from women who ended up getting breast cancer to the blood samples of women who did not get breast cancer. So the individual studies ranged from about 100 cases to almost 1,000 cases. And if we look at the relationship, this is using beta-carotene as an example, and here are the individual studies at the bottom. And actually, the CLUE studies are part of the study that Dr. Garland mentioned, collecting 25,000 blood samples for. So across these studies, we can see that several of them had seen inverse associations. This is the top. This is sort of funny writing at the bottom here. The top versus the bottom quantiles for each particular study of beta-carotene. So again, you could see across the literature, there were several studies that showed an inverse association, but they weren't necessarily consistent with respect to which particular carotenoid. And some of these studies had seen associations in one particular subgroup of women, but not another. So at that point, I thought it would be interesting to try to pool this data together to be able to look at more of a larger analysis of this. Now, one challenge with doing this, of pooling data, so that instead of doing a meta-analysis where you pool together the results of the studies, this is actually pooling together the raw data of the studies. But one challenge with doing this is that the carotenoid levels have varied across the studies. So I'm giving you an example here of two of the cohorts that we included in our analysis. One is the women's health study that's based at NYU, and then this is a women's health study that was based at Harvard. Now, demographically, these populations are quite similar. And so we can think that they likely have similar lifestyles, perhaps similar diets. And if we look at some of the relationships between the individual carotenoids, we can see that the NYU Women's Health Study has slightly higher alpha-carotene levels than WHS does, but they're pretty similar with respect to their beta-carotene intake. But then if you look at the levels of lycopene in the blood, the NYU Women's Health Study has more than four times higher levels of lycopene than the Women's Health Study, which, given the very similar demographics and likely very similar diet and similar levels of the other carotenoids, this sort of stood out to me as seemingly unlikely. So this is one of the challenges of how do you pool together these data when the distributions are very dissimilar, but you are not sure that that's actually reflecting the truth. So what we did was we collaborated with the investigators of each of these original studies, and we asked them to send us from their archive collections of blood samples 20 samples from the original study, so that we could put together 20 samples from each of these 8 studies and analyze them together at the same time in the same lab to try to understand what some of these differences were. So you can see this is for, even within our cohort in the Nurses' Health Study, we had measured the carotenoids in a few different batches over time. And looking at some of the batches, we saw good correlations over time, but quite different absolute levels. So even within our own study, we needed to do a bit of standardizing and recalibrating. So, but as you can see here, this is the correlation between the original assay value and what we call the drift or the rerun assay value. So again, this is within one of the batches of the Nurses' Health Study samples, and you can see that the absolute levels are quite different between the original and the rerun. But the correlation, R-squared, is 0.96, so the correlation between these is quite good. And this is a study from Umeå in Sweden that showed, again, very good correlation between their original levels and what we had done with the rerun samples. So I wanted to show you a couple of examples here. So one of the things that we wanted to try to achieve was to standardize the blood levels across cohorts, but also respect the fact that there may be population differences between the studies that we wanted to maintain. So as an example, we can look here, SWHS is the Shanghai Women's Health Study. So these are women in Shanghai, and you can see in the graph here, these are the medians of the original value in their study, and these are the medians after we recalibrated their study. So you can see that they're still very high in levels of lutein zeaxanthin, higher than the other cohorts. And in contrast, in both the original value and the recalibrated value, they're very low in lycopene levels. So this reflects probably true population differences because lutein zeaxanthin are high in leafy greens, which is a big part of Asian diet. But there's not a lot of big tomato consumption in China, so they are naturally quite low in their lycopene levels. But if you remember, the Women's Health Study had this, seemingly, to me, quite odd low level of lycopene. And when we recalibrated that measure, they became much more similar to the cohorts that we would have expected them to be similar to. So instead of being as low as Shanghai, they actually were much more comparable to US populations. So this was a way that we were able to maintain true differences between the populations, but also get rid of the noise that happens with lab measurements and lab variation. So just briefly, this is what we ended up with: about 3,000 cases and nearly 4,000 controls. majority of them were postmenopausal women, and there was a mean time of about 4 years between the time of blood collection and the onset of breast cancer across the studies. So to look at some of the results, this is showing in successive quintiles. So the top is the bottom quintile, so low levels of the carotenoid, and here the fifth quintile of carotenoid level, again measured in these blood samples. And you can see a trend of inverse relationship between higher carotenoid levels for alpha carotene and beta carotene and risk of breast cancer. So this is about a 13 to 17% lower risk for the women who are in the top category of these carotenoids. And we saw a similar trend for lutein, zeaxanthin, as well as lycopene. And when we summed these to a total carotenoids, we can see about a 20% lower risk of breast cancer for women who are in the top quintile of of the total carotenoids. And we looked by ER status of the tumor, as we had seen in the dietary pooled studies. And here you can see that in the blue bars are the ER positive tumors, and in the red bars are the ER negative tumors. So there's maybe a suggestive lower risk of the ER positive breast cancers, but really more of a strong inverse association between higher levels of carotenoids and the ER negative breast tumors, which are more aggressive breast tumors. So this is looking at quintiles of beta carotene, and we saw similar differences between the ER positive and the ER negative for the alpha carotene as well. Now, one of the advantages of having lots of data is to be able to look at effect modification. So are there factors about a woman's lifestyle that might modify the relationship between plasma carotenoids and risk of breast cancer? So one of the things we looked at was smoking, and we had hypothesized that various exposures that are related to oxidative stress in women who had these exposures, they might be the ones that might benefit more from higher levels of carotenoids. So here you can see that among non-smoking women, there's maybe not a significant inverse association with carotenoids, but among the smoking women, there was a significant inverse association. We also looked at BMI, thinking that this is, again, could be a source of oxidative stress. And what we saw here was in the blue bars, these are the lean women with a BMI less than 25, we see an inverse association between carotenoids and breast cancer. And in the red bars are the overweight women, where we seemed to not see an association. And then the green bars are the obese women. And surprisingly, we had seen a positive association between carotenoids and breast cancer here. So this goes opposite in the direction of what we would have hypothesized. So that felt that this is something for sure worth exploring a little bit more. But given that carotenoids are fat soluble, and women with higher BMIs tend to have lower plasma carotenoids. So it begs the question of how an obese woman ends up with a really high plasma level of carotenoids. And is it possible that these women have massive amounts of carotenoids in their adipose tissue? So it's something, as I said, worth exploring further. Sort of gave us pause as we had seen these results. So I've done a couple of other studies since then, looking more into details about the timing of carotenoid exposure, as well as looking at the tumor subtypes. So combining the Nurses' Health Study and the Nurses' Health Study 2, we did an analysis focused really on premenopausal women. As I've mentioned, the pooled analysis was mostly postmenopausal women. We had looked at whether there was a difference by menopausal status, but didn't appreciate one. So we, with about almost 1,200 cases here, we looked at the relationship between plasma carotenoid levels in premenopausal women at the time of blood collection and subsequent risk of breast cancer. And a little bit surprisingly, we did not see the same associations that we had seen in the pooled analysis. So these carotenoid levels, this is looking at by quartile of carotenoids, were not strikingly associated with a lower risk of breast cancer in these premenopausal women. One of the things that we looked at was whether they were premenopausal at the time of their breast cancer diagnosis or postmenopausal at the time. And for some of the carotenoids, including lycopene, we had seen that there was a suggested inverse association among the women in red bars here who were postmenopausal at the time of diagnosis. So this, and didn't really see anything in the women who were premenopausal at the time of diagnosis. So this leads us to try to think about, well, is it a question of the timing of exposure, that the women who were postmenopausal at diagnosis were actually measuring their carotenoids earlier in life, or is there really a difference by menopausal status? And I would honestly don't know the answer at this point. So I think this is another area that is worth exploring. So in the Nurses' Health Study with our 2 blood samples, we've done an analysis looking more specifically at this time between when we can analyze blood samples for carotenoids exposure and the time of their diagnosis. So this includes about 2,000 cases and 2,000 matched controls. And among almost 600 of these, we have a second blood sample that was collected 10 years after the first blood sample. So here, across the board, we can see inverse associations between the carotenoids. Beta-cryptoxanthin tends to not show up in most of these analyses, but alpha-carotene and beta-carotene, we can see inverse associations between the highest levels and lower risk of breast cancer. Lutein zeaxanthin is suggestive, but not really significant, and you can see it in lycopene and total carotenoids as well. And then when we look by the time between the blood collection and diagnosis, in the blue bars, this is blood samples that were measured within 10 years of diagnosis, and in the red bars, blood samples that were measured between 10 and 20 years prior to diagnosis. And what you can see here, without this little blip here, we can see for both of these, it's suggestive of an inverse association between higher levels of carotenoids and risk of breast cancer. And suggestively, maybe it's a little bit stronger with the levels that are measured longer ago. But this suggests to me that it may be important at multiple time points before the progression to breast cancer. And you can see here is for the association with total carotenoids. So then, coming back to the subtypes, we looked by ER status in this analysis of the 2,000 breast cancer cases from the Nurses' Health Study. And we did not find the same difference between the ER positive and the ER negative cases as we had seen in the pooled analysis. But in one single study, even though we have 2,000 cases, there are fewer ER negative breast cancers. But we do still see a suggested inverse association with actually both subtypes here. Then using some other metrics to be able to look at aggressiveness of the tumor, we found looking at differentiation. So how well differentiated are the tumor cells, with the well differentiated being slightly more normal looking than the poorly differentiated. We see a stronger inverse association for the more poorly differentiated and therefore more aggressive breast tumors. When we looked at luminal A versus luminal B, in this subset with plasma, we didn't have enough to be able to really look at the triple negative and other subtypes, but we do see a stronger inverse association for the luminal B tumors, which are slightly more aggressive than the luminal A tumors. Then we also, since we continue to follow these women, we looked at whether the breast cancer that was diagnosed in that particular woman went on to either cause death or went on to recur. So when we look at the relationship between all breast cancers and carotenoids in the blue bars, the inverse association that I'd shown you earlier, and then in the red bars, these are the tumors that actually caused death or recurred. And you can see that there's an even stronger inverse association between higher levels of beta-carotene in this example and risk of these quite fatal tumors. So revisiting some of the associations that we had seen in the pooled analysis, we wanted to look again by BMI. And similar to the pooled analysis among the lean women, we see an inverse association between carotenoid levels and risk of breast cancer. And in the overweight and obese women, we don't see the same relationship. We don't see an association, but we also don't see that positive association that we had seen in the pooled analysis among the obese women. So this makes me feel a little bit better, but I still think there's more to be explored there in terms of the biology of what's going on. So I wanted to finish up by looking at some of our more recent findings in terms of diet and breast cancer, looking at fruit and vegetable intake, just because there's more to explore in terms of the timing of exposure. So we know from some of the other breast cancer risk factors that there is this window of susceptibility in early adulthood or in adolescence that contributes to a woman's later risk of breast cancer. So one of the ways we've looked at this is in the GUTS cohort, which is the Growing Up Today study, which includes the children of the women who are enrolled in Nurses' Health Study 2. So we enrolled these kids. They're now no longer kids, but between the ages of 9 and 17. And so we have about 28,000 of these kids that we have continued following. But of course, now they're in their 20s to early 30s. But we captured their dietary intake during adolescence. And in a younger population, we can't quite look at breast cancer incidence yet, but we can look at benign breast disease, which is a precursor and a strong risk factor for the development of later breast cancer. So, it's a little bit fuzzy here, but it suggests that women who had higher intake of beta-carotene in adolescence are at a lower risk for benign breast disease. And then, as I noted in Nurses' Health Study 2, we did collect information on the women's diets during adolescence, and then they were enrolled at the age of between 25 and 40. So we have their dietary information from early adulthood as well. But looking at the adolescent diet, we can see that adolescent, particularly fruit intake, we saw it with fruit intake more than vegetable intake. There's an inverse association between higher fruit consumption and risk of breast cancer. And similar to what we've seen with some of the plasma carotenoids, there is a difference whether the tumor is hormone receptor positive or hormone receptor negative. And we're seeing stronger associations with these more aggressive hormone receptor negative tumors. And then combining the two cohorts, we're now doing more with the dietary intake that we have collected over now 40 years in the Nurses' Health Study, and can look at fruit and vegetable intake and see an inverse association between total fruit and vegetable intake and breast cancer risk. And coming back to Dr. Ho's talk earlier, we're also starting to see an inverse association between cruciferous vegetable intake and risk of breast cancer. And sort of highlighting the carotenoids again, looking at yellow and orange fruits and vegetables here, we can see an inverse association with risk of breast cancer. And similarly, when we look at subtypes, we can see for both fruits and for vegetables that there's a stronger inverse association for the ER-negative tumors than for the ER-positive tumors. And when we look by the molecular subtypes, we have a little more power in the full cohort using the dietary intake. So we can see for fruit and vegetable intake, stronger inverse associations for the HER2 and the basal-like tumors, which again are the more aggressive tumors. We don't see much with the luminal B tumors. So to conclude, while we have identified several breast cancer risk factors, there are a few of them that are really modifiable. And in terms of the more aggressive subtypes, there are even fewer that have been identified that are modifiable. So what we can see is that carotenoids are associated with a lower risk of overall breast cancer and the aggressive subtypes of breast cancer, as well as looking at the breast cancers that ultimately cause death or recur. And we can see that exposure across the life course does seem to be important. And I think that this breast cancer evidence sort of adds to the many health benefits of a diet that's rich in carotenoid-rich fruits and vegetables. So it might be one more factor that might convince people to eat a little more healthfully. So I wanted to thank all of my collaborators, both across multiple institutions for the pooled project, as well as collaborators within the Nurses' Health Study and Nurses' Health Study 2. So I hope that you take home the message that breast cancer might be one more reason to recommend a diet high in colorful fruits and vegetables. So thank you very much.